All right, so I think we should be good to start. Give us a minute. We're trying to live stream, same on the YouTube as well. Right, so good. Looks like we're live on YouTube. If there are participants who are attending, they can also just take a look at this session online as well. All right, so great. And let me also, Vinayak, could you record the session as well? Or let me just do it so that I can upload. All right. Good evening, everyone. Warm welcome to all of you to the session, which is day one on the Certified Bootcamp on Electric Vehicle Powertrain. I'm Suraj. I'm the course director, and I'm also the co-founder and CEO of Decibels Lab. It's always gives us a great pleasure to invite participants from across the country and also from different countries as well. So where we share our knowledge through this series of bootcamps, right? So I will just give you a heads up on the overview of the bootcamp so that, if you have any queries where you're currently landed out, you will have a clarity on all these things. Okay. So basically, you would have got registered to some of these programs because there are multiple programs. So you come to our website and then just land here. You would have taken up all this, overview of programs that are available here. So we have program that got finished yesterday on lithium ion cell chemistries and characteristics. And if somebody has missed out, there is a YouTube channel. We can also view it there. Today we are starting the electric vehicle powertrain bootcamp. Right. So like in similar, we have one bootcamp that is on 18 July. That is like a lithium ion cell modeling approaches and state estimation algorithms. If somebody is interested on this, you can definitely, because somebody was asking me, I think Vinod or somebody. So you can also look forward and take up in this program as well. So let's get started with the first one, this is a batch 3 of our bootcamp. It means we've already done the 2 batches. So the overall idea is the 3-day program, and we will also have a hands-on learning experience as we go ahead for the next days. And today I'll be taking a session. I'll be covering about all the components, subsystems, technologies of EV. Then tomorrow, Mr. Krishna will take up the session. So he will cover up the sessions in the areas of, hand calculation, motor sizing, battery sizing, energy calculations, and stuff like that. Then on the day 3, which is module 3, Mr. Srinidhi will take the session. So he will cover up on the basics of vehicle testing, and how do you collect the data from the vehicle, and how do you make a meaningful sense of the data and stuff like that. Okay. So that's how it's going to happen. So it's free of cost, anybody who have registered. The certificate is only given for participants who attend the live classes every day. Okay. So you have to take part in the session for all the 3 days so that you will be able to get a certificate. So people who doesn't attend the live classes, you will not be able to get a certificate. So that's just a heads up for the whole course. Okay. Awesome. So then we will get started with the course directly. Okay. Great. So let's get started because I see a lot of people have amazing interest, and good to see all of your questions right everywhere to discuss about the whole topic here. So from my side, let me just start with the first topic, right? So we would like to know how EVs are eco-friendly, right? Everybody thinks that EVs are great. They save a lot of emissions. It's eco-friendly, like a lot of these things, right? So, but how do we justify lithium extraction creates a lot of emissions? Lithium getting disposed into the atmosphere, our environment, or our water bodies would create contamination. If you take an example, like batteries have a specific life, so they need to be replaced after 6 years, 7 years, or something like that. So what not? I mean, in continuation to that, you need to charge the vehicles. The energy come from your coal power station, so you make a lot of emissions. Already we have less electricity available, or improper grid structure that is causing a lot of losses. So there are a lot of problems, right? And when you see through EVs that we say as eco-friendly. So I would like to know from your side that how do you justify EVs are eco-friendly? Okay. Anybody have an answer to that? Anybody have an input to that? You're welcome to have a debate. Have a quick discussions on this. Let's not take too much of time, and I have a lot of topics to deliver. Let's take about another 3-4 minutes to discuss on this one slide. Anybody can justify, how do you say EV eco-friendly? Because the whole world is looking forward to transition to EV, right? So how do you justify?
EV is eco-friendly when we use our the power which we are recharging the battery should come from natural. Like if solar or wind, or if it is contributing to charging the vehicle, I think that makes sense. Lesser emission from compared to the smoke which we are generating from thermal plant, and the power we are utilizing for recharging, that efficiency is also getting down. But when we do from this battery, obviously the battery has a lot of contaminated which can do the harm to the earth. But if you overall talk about life of the overall emission, then EV can dominate that.
Good, great answer. Thank you for participating in giving the answer. I would like to prove that analytically, by the numbers and figures, because we're all engineers. So we would like to arrive at a conclusion that, okay, if you say eco-friendly, okay, what is the value? If I run a bike by 1 kilometer, like an Activa, if I run an Ather by 1 kilometer, if I run that charging with the solar, if I run by charging with the fossil fuel based thermal power stations, so I can prove it, right? So until and unless we prove it, so we won't be analytically able to justify. Great. And also I see a lot of interactive answers in the chat box as well. So they do not emit pollutions. Yeah, they do not emit pollutions at the tailpipe, but they also emit emissions in the different locations, right? So not 100%, since they still power generation depends upon the gases. Okay, so it can be options like solar, wind turbine. It's time to eco-friendly because electricity generation is from thermal, not clean, even make situations even worse. Okay, interesting questions. Wheel to well analysis is less, but the battery to wheel efficiency is much better. Although still the percentage of energy generation is still based upon how the sources has been used. Awesome. So wow, that's a great number of answers. So the emissions are minimum, but electricity production still create pollutions. Decreasing the fossil fuel consumption, so we need to choose alternative methods. Awesome. That's a fantastic, very mature kind of interactions. So great. Let's get started further. So here I would like to say that, okay, we as an engineer, right, we have to prove things analytically. And how do we justify this is true, correct? Newspapers can tell us, okay, hey, it's eco-friendly. Everybody can just publish some information, just printing some documents, right? But we need to kind of think it analytically. So I take you through the journey of hand calculation so that we can prove by end of this few minutes that, okay, hey, I can justify it as eco-friendly, right? So before that, I just give you an idea on something like wheel to well, right? And wheel to tank. Okay, there's an analogy like this. So let's say you actually first extract coal, right? So you make emissions. You transport a coal, you make emissions. You convert a chemical energy into a thermal energy, you make emissions. And then you convert a chemical energy into an thermal energy into an electrical energy. You then transport the electrical energy. Across the transportation, you do a step down, step up, you lose some amount of energy. It comes to your home finally. When it comes to your home finally, right, you need to charge it. So what does your charger do? It converts the AC that is coming into your house from the grid into a DC. So there is a conversion loss again. Then you feed that DC to the battery. The battery stores the energy in a chemical format again. So it is converting a current, which is electrical, then to a chemical energy stored in the battery. Again, it converts back that chemical energy into electrical energy when it is discharging. So there is a loss. It means called charging and discharging loss. Once it converts from that format, it goes into the motor controller. Again, in motor controller, a lot of EVs, we use AC motors. So you need to again convert that into a AC. So you need conversion requirements. Then you do some losses. Then you finally send it to a motor. There you convert an electrical energy into a mechanical energy. Obviously, you do some amount of losses. Then finally, it goes to the wheels. That is where it is basically driven mechanically to the vehicle. So when you just walk through all of this long journey, right? So there is a lot of emissions that you could do, completely from the starting point to the end point. Okay. So when you make it happen, somehow, how do you justify with all these losses, with all these problems, all these inefficiencies? So how EV are eco-friendly is a question. So now let's go through the next slide. I would not say again much blah blah here. So you already know there's a lot of ways how we can produce energy, get an energy. You can convert that one form to another form. So then you can charge your vehicle in place. The very important thing that we need to understand here is something like a well-to-wheel, a topic of discussion, right? So if you take a discussion for topic like this, so there is a well to pump, right? Well to pump, and then well to wheel, and then pump to wheel. This is the three typical analysis that will give you an idea that, okay, what kind of analysis I should do so that I will be able to justify the EVs are eco-friendly. If you do between this, right, if you do between a fuel tank, consider this to be a charging station, and then electric vehicle. So EVs are awesome. EVs are like, most eco-friendly elements in the world. But the problem also lies is, it is not that you just don't make emissions at the city or when you're driving at a tailpipe, but you also make emission across the whole bandwidth from the production of electricity or extraction of materials, right? Like if it is a diesel and gasoline, it will be from the crude oil. If it is a electricity, then it will be from either thermal power stations from coal, or based on natural gases, or it is also based on various different sources of nuclear or stuff like that. So you're also making emissions in all the line across, right? So you're basically supposed to identify that what is the source to get the energy started. Now there is also a data available that, okay, this is what it is if you actually drive like a mid-sized car, means something like Swift. So over about 12,000 miles and about 20,000 kilometers, if you drive, it says that, okay, you will produce this much of carbon, CO2, this much of NOx, this much of PM. But if you charge the EV by grid, right, you are expected to produce this much of emissions. But if you do with renewables, it says that you don't make any emissions. Okay, this is not true. This is, if I go back, this is a analysis that is done, which is between this to here, right? It is not the analysis from here to here. It is between this to this. So with that way, it proves that, okay, EV is eco-friendly, right? So now we have to somehow kind of prove this, that how it is more eco-friendly with respect to our calculations. There's another slide where I wanted to highlight that why we are focusing on a transportation segment, right? Why are we focusing on a transportation segment? To electrify. We can electrify industries, we can electrify different things, right? Already our house is electrified because of all the electricity that we use for applications. But in transportation, if you see the amount of energy produced, amount of energy consumed, right? If you see, the transportation sector consumes highest amount of energy, right? So because of that, if we electrify that sector, then we will be able to reduce a lot of emissions. So that's the goal why world is focusing towards electrification of automotive sector. Now let's leave that and go to the next topics. So there are here very simple set of calculations here. Okay, so let me just correct this one topic so that you can get to know what I'm trying to make corrections here. So this is 75 kilometers. So let's kind of correct that. Save this and then. Okay, I believe everybody can see my screen. So let's start with one by one. I mean, if you can do also hand calculations, that's also good along with me. The first important thing from this side is.
Right, Bajan,
Yeah.
Screen is not shared.
Oh, is it? Okay. All right, sorry. So if you see here, right, so this vehicle, let's take something like highlighter. Yeah, let's take a Activa Honda, right, and then take an example of Ather. So they're almost like a same benchmark vehicles. It means the Ather could perform as similar to Activa Honda, right? So that means they are in a similar competitive environment. And if you see a comparison of range, let's consider it gives 50 kilometers per liter. In reality, it may not be. The same way with the Ather as well. In reality, it may be even less as well. But let's consider that they will give that much of range for a 1 kilometer for a single charge. Now let's go with the calculations. Petrol's calorific value is 9528 watt hour per liter. Correct? Then if you go back here, average energy consumed at the wheel to the details here. So how do we do it? It is calorific value of the fuel by range. So you get 190.56 watt hour per kilometer. So you consume about 950.56 watt hour per kilometer. Now we have to include, this is basically tank to wheel, right? Because you're not considered any emission, so energy consumption, including the loss of transportation or a refinement. So now if you consider that, it's about 67%. How do I find this number? It's taken from some of the ministry sources. You can check out in the website as well. What is the refinement losses that we have in a country-wide or a global-wide? So it's about 67%. It means the efficiency is about 67%. The loss is about 33%, right? So if you do the math, then just this basic one, right? You will be able to come to a conclusion that the vehicle will consume 284.4 watt hour per kilometer, including the inefficiencies of a transportation and a production of fuel. Let's consider that as a petrol now. To make a same comparison here on this side, right? So range is 75 kilometers. The battery power is 2.4 kilowatt. It's about 2400 watt hour. So now energy consumed at the wheel, how do we do it? Battery power by range. So if you do that, the Ather only consumes somewhere about 32 watt hour per kilometer. So we need to also include something called charging and discharging efficiency. I might have already explained to you that when you charge your battery, you convert an electrical to chemical energy. So when you discharge it, you convert a chemical energy into an electrical energy. In this process, you have lost some amount of energy, right? That is basically your this efficiency, 80%. It means it's 20% inefficient. If you put that math, you make about 40 watt hour per kilometer. Then there's a data available that production and transmission efficiency of electricity, it is about 70% inefficient. It means it's 30% efficient. So it means very bad. Efficiency of the electricity production is quite bad. I again got this data from references. If you put that math into a place, then what do you get is 133 watt hour per kilometer. Let's mark this in a different color, right? And this is the data. So you consume about 284.4 watt hour per kilometer. Here you consume about 133.33 watt hour per kilometer. So you already see the Ather consumes less compared to Activa in terms of energy consumption per kilometer. Any questions from anyone till now? Okay, can we record this session? Santosh, this session is live streamed. It is also available on YouTube. Okay, nothing to worry, you can watch it anytime. Any questions from anyone? Okay, so we see that there is no questions. Now let's move ahead. This is the same comparison between Tata Nexon and Tata Nexon EV. Right? This can be an awesome, perfect comparison somebody can do because it's the same brand, same vehicle segment, same comparisons. So you can also see that the petrol version of a vehicle consumes about 836. The electric version consumes about 420 watt hour per kilometer. So that means it is almost half, right, in terms of energy consumption. Now let's start to calculate the emission. We know only the energy that is being consumed, right? But we also need to calculate the emission in terms of grams of CO2 and different parameters in place. So again, there is a math that I have done here. So CO2 content of coal is 660 grams of carbon per kilowatt hour. CO2 content of fuel is 530 grams of carbon per kilowatt hour. So this data I have got it from some research papers and PhDs. So this is believed to be correct, and I also compared with a lot of resources. That data is pretty accurate as well. So if you want to produce about a 1 kilowatt output, then you have to burn about you would burn about and create about 660 grams of carbon. If you want to make about 1 kilowatt of the output, then you need to create about 530 grams of carbon, by burning X amount of fuel or X amount of any energy for other requirements in place. Now let's go and substitute the data here, right? Because what you have got here is watt 284.4 watt hour. Let's consider this is 284 itself, or this is 133. Now, if you compare the data back here, so if you plug the value to this requirement, because if you make 1 kilowatt, then you make 660 grams, but it is not 1 kilowatt, right? So the requirement is only 284. If you make 284, then you make about 150 grams of CO2 emissions. The same way, if you do with Ather, right? Ather is consuming 133.33 per kilometer. It is going to make you only 88 grams per kilometer. So when you do this comparison, even if the vehicle is charged, even the vehicle is charged with a source of energy that is available from coal, right? Thermal power station, still EVs are eco-friendly, right? Still EVs are eco-friendly, because if you see the values here, it hence proves that EV is eco-friendly even though you charge the electric vehicle with the help of thermal power stations compared to IC engine vehicles. Okay, almost like a reduction of 70% emissions. The same way, if you compare Nexon with electric Nexon, you are making very much less emissions compared to petrol vehicles. And now this is a one section. Also, along with this, EV have other advantages, right? You don't have to replace engine oil every 10,000 kilometers, 8,000 kilometers. When you make engine oil replacement, obviously you will have emissions because of oil also. You need to manufacture that oil. Other thing is the oil that is already there in the engine need to be thrown away somewhere. So there is an emission. Apart from it, there are a lot of moving parts. That would be a problem because they will wear and tear very quickly. You need to replace them. And additionally, along with all these things, you also have a problem with thermal heat being dumped into the environment because the engine is inefficient. Thermal efficiency is somewhere about 28%, 35%. You're dumping a lot of heat into the environment. That is also a problem, right? So, but in EV, that problem is not there, right? That is an advantage. But the problem is the batteries may be an issue as well. But you can recycle the batteries. After 6 years, 7 years, you can recycle the batteries if you properly do the recycling process. But that is not a case with petrol engines or gasoline engines, because you will, once you burn fuel, it's gone, right? It produces carbon and different emissions along with the heat as well. So you cannot recover that back, right? So that's the advantage and that's the disadvantage between a gasoline system and or a diesel with respect to electric vehicles. So now, any questions from anyone? How clear it is now? How crystal clear it is now that you're able to prove that EV is eco-friendly in place, right? So any questions from anyone? I have given you an option to unmute as well. You can interact live. Prashant Kumar, we also have to consider the production emissions of electric vehicles, because EV production emissions much more than a petrol or diesel one. Okay, interesting question, Prashant. Maybe we may have to think to that angle as well. There is no doubt as a person. So you can definitely think and consider that values as well. But I considerably feel that it would be definitely comparatively advantageous still, even having that. But again, can I prove it now? Maybe I will not be able to do it. But yeah, I don't have a data, so we can check it out. How did estimate the average consumption? I'm sorry, where average consumption, we have gone through the calculations. I believe it was pretty clear on how did we arrive at these values. Okay, so any questions from anyone? Right, so will we get a PPT? Sorry, we don't have an option to share it, but yeah, these videos are available on YouTube as well. Okay, so awesome. Then we are pretty clear at this stage that why EVs are advantageous compared to IC engine vehicles. So with this note, we can move ahead quickly. Again, any questions from anyone? We can still have a debate on that. Okay. So as of now, no questions from anyone. Then we can move ahead. So just before I start ahead with the session, so I just want to show you also our. I think some people have a confusions on where they can find their these videos later on, in case you are able to watch them later. So yes, so we have our YouTube channel. It is called Decibels Lab. I can share this YouTube channel as well. I can also share this link so you guys can keep this link along with you. So in case you want the link, you can watch the video in this link. Okay, so this is a link where we are live streaming this video, and also our YouTube channel is available. You can check out our YouTube channel. This is our YouTube channel where we have kept other videos as well. So I will just share this link across to you. Yes, if anybody are interested to watch them later, you can actually just check out the channel, and you will be also able to watch the videos as well. The one we are doing now and all the ones that will be done tomorrow, later tomorrow, will be definitely be there. Nowadays, we see there are some cases where EVs are catching fire. So, okay. So there are a lot of reasons why EV catches a fire, right? So it is from different detailed approach how you can justify that the fire has been happened. It can be because the battery quality itself can be bad. Okay, there is an internal issue in manufacturing. You may get some defect pieces, right? So typically when we call 6 sigma quality, 5 sigma quality control, even though it is 5 sigma, it's about 96%, you still have 4% of error or defects, right? If it is a 6 sigma, then it goes much higher. In these cases, you still have a defective cells at a typical level, right? On the other side, you could talk about safety engineering. Okay, one, mechanical safety, second thing is electrical safety. So if the cells are not integrated properly in a mechanical way, it could be as a mechanical structure or thermal also, because that's part of a mechanical side, right? So there could be issues on it is not, the heat is not properly dissipated, or there's no proper mechanical integration that cells has been kept in a proper place. Then the other side, okay, where do you have to exactly keep the fuses? Where do you have to keep your exhaust in a battery management system? What kind of data you're collecting? Does your battery management system gives you a proper protection, right? So a lot of these things comes into a picture when you talk about thermal issues. Largely because the issue starts at a cell level. Okay. On the other side, did I choose a right cell for my application? Did I test enough before I put the product into the market? A lot of these things comes into a picture. It is not just like, okay, there is some issue with the coolings and stuff like that. If you see Ather, right, they don't have a liquid cooling as of today, right? But you have just seen the one incident. That is because the vehicle met with a crash, and somebody washed the car and the bike, and then the fire caught in. But yeah, if you see, largely there was no case, and they don't have a liquid cooling, advanced cooling, and all these things. It's just a better design. right? So it depends upon, what kind of stuff that you want to put it in. Can this knowledge help us to build a racing vehicle? Assume that there's little differences from other commercial vehicles. Okay. There are a lot of difference from other commercial vehicles. Absolutely, there can be a lot of differences too. There's no doubt on that. The cells used for racing applications are largely different. The cells, the way of thermal management is different. It's quite definitely different than compared to normal vehicles. No doubt on that. Okay, so I think, no questions from here. So we'll just move ahead with the specific topics of this. So I can just take one slide and continue the whole session, or we can go through multiple slides as well. So everybody knows what is there in EV, right? So we start with the first component. That would be the transmission, and then the motor, then the inverter, then there's an onboard charger, there's a DC-DC converter, and there's a battery pack, right? Then there's a battery management system. Then there is a heater that can heat this battery pack in case that is required. Then we also have a compressor, which is basically your air conditioning system, right? HVAC system, heating, ventilation, and air conditioning, right? So this is what largely any electric vehicle will contain. Okay, if you talk that if the vehicle is two-wheeler, then you may not have a HVAC system, right? But the rest of the all components will be definitely present in the vehicle. There is no difference that heater is equal to cooling system. No, that is a completely different one as well. I can explain you in the further slides. So any clarifications on the components? Okay, so now let's take some questions. Why do you think the transmission is required, right? So why do you think the motor is completely different compared to a normal applications? What is the function of a DC-DC converter, right? What is the function of battery management system? So like this, we're going to discuss in the next couple of topics so that we will be able to derive into the details. Inverter is basically motor controller. Yes, that is correct. It's called as traction inverter in some cases. It's also called as a motor controller in general. Okay, so now let's go to the technicalities of the details. So why do we have an onboard charger while we have got an off-board charger given by the company? Okay, so there is a data here that is, we also have a normal charger. We may have a fast charger as well, right? The quick charger, which is mentioned here. So we have a quick charger. We also have a normal charger. See, when you see a normal charger, right? So what does mean normal charger? If you take your household applications, the maximum rating that you get is 15 amps from the large socket, like an AC socket, which we typically call, right, the big ones. So the typical rating of that is about 15 amps, correct? So that means you're drawing 15 amps. What is your voltage? It's 220 volts. So 15 into 220 is somewhere about 3.2 kilowatt, right? 3200 watt. That means when you want to charge a bike or a bus or a car at your house, the available input is somewhere about 3.3 kilowatt. It means you cannot have a charger bigger than that, right? This charger cannot, this onboard charger, if it is bigger than that, there is no use because your available input itself is limited, correct? So onboard charger has a limitation. It means it is typically a small one, below 3.5 kilowatt, 3.6 kilowatt size, because in other countries like UK, Europe and all, the current ratings are slightly different. They have even up to I think 120 volt also. They have 220, they have also 360, something like this is different. Okay. So that is why there is a level 1, level 2, level 3, all these kind of concepts in place. But the idea is the onboard charger means it is having a limited output compared to off-board charger. The objective of the off-board charger is off-board charger can be very large. It can give you like 150 kilowatt, 150 kilowatt, right? Compared to onboard charger like a 3 to 5 kilowatt, right? So in these cases, there is a limitation. It means if you are charging a battery of 35 kilowatt with a 3.5 kilowatt charger, ideally it takes 10 hours, but in reality it takes about 12 to 13 hours, right? But if you charge with a fast charger, your battery will only just take about, if you're charging with 150 kilowatt, it doesn't mean that, it will charge in, 15 minutes or something like that. It also depends upon the ability of the battery to undergo fast charging. So depending upon that only, you can do you can have a 100 kilowatt charger, but you cannot use all of that to give it to the battery. So there is a limitation. Let's say the battery pack is 200 volt, and the charge current is somewhere about for 0.5 C, or let's say even 1 C. That means you can charge it with a 200 Ah battery, and if you can charge it 1 C, then you can supply 200 amps, right? So if it's a 200 volt, and then you can charge the battery at 1 C, and the capacity of the battery is 200. That means you can go 200 into 200, right? So that means you can go like a 40 kilowatt charging. So it's a way that how you could just put your systems in place for the requirements. Why charger is only connected to, okay, as I think I explained you, Sakshi, why it is done. I think Rahul, you got an idea that why it is so. The auxiliary unit is equal to AC compressor. Okay, auxiliary unit, you mean this is a AC compressor, right? Auxiliary units, where did you see apart from this? Okay, see, it is auxiliary units can be your headlights, right? Obviously, anything which is non-tractive is basically your auxiliary load. So again, in the auxiliary load, you can define what is lighting load, what is compressor load, what is heating load, what is load for the electronic systems, blah blah. You can also start to define all of them. Maybe for power windows, power mirrors, right? All of them run with a electrical input, right? So they can be called as auxiliary loads. Any questions? Okay. So now if you see through, let's just erase everything and then come back. Okay. So now let's talk about component in detail. If we have two set of batteries, how charging works? See, I mean, if you have two set of batteries, means if they have not connected together in the internal structure, obviously you have to charge them separately. How efficient is regenerative braking system in EV compared to one in IC and vehicles? Okay, by the way, you do not do regen in IC engines, right? So there is nothing you can use as a regen. Largely you can do it in Formula One, like KERS, like kinetic energy regenerative systems, but not in general vehicles. How efficient it is in EV, it depends upon a lot of control strategies. It is good. It is definitely beneficial, but if you have enough amount of technology to back it up. How CAN connects with each unit? Okay, see, CAN doesn't necessarily connect with each unit. Good questions, matured questions, happy to answer always. See, all of this battery pack can have one BMS, right? So this is here. So this BMS can communicate electronically with another unit, right? Let's say this is your main ECU, right? So the BMS can send only some amount of data through CAN, right? So you don't need to send all the data through CAN. What ECU wants only that much of data, the BMS will send through CAN. Then the motor controller, if you take an example, right? What is required, that information the motor controller will send. What onboard charger will require, that onboard charger will send. So it means they are all connected through a network, which is basically like a CAN network. You can individually run the wires, but typically in some scenarios, you could have like a master to slave, something like that. Okay, you can have one master and then you can have multiple slaves. So you can send the data from inverter to onboard charger to a BMS. BMS will send the data to a ECU, or what we can call as a centralized gateway, which will be a VCU, vehicle control unit also in some cases. So it depends upon how you want to set your architecture, but largely it may be independent, it may be dependent as well. So you may have some data from, body control unit, like a BCM, right? The BCM will send a data to a VCU, which is basically nowadays VCU acts as a gateway for everybody, right? So, or you can have an infotainment cluster. So you need to display your SOC, right? Which is basically battery's capacity and stuff like the battery temperature, your vehicle speed, and a lot of regenerative mode, all these things. The data come from ECUs like BMS or inverter, which is basically a motor controller. The data you get from there is pushed through a gateway, and the gateway will send the data to a infotainment system. So it's a way you can put across how you want it. I think it's clear for you on how is it done. Okay. All right. So now, why do we need a transmission, right? So again, rather than going to too much width of the topic, I'll go to a depth of the topic. Now let's take a one, maybe what I can call it as a whiteboard. So let me just exit the stop sharing. Let me just share a whiteboard with you. Yeah, I believe you can see a different screen from my side now, right? Yeah, okay, great. Then you are able to see my screen. So now I will give you an option to unmute as well. And yeah, you can let me know, why do we require a transmission? What is the need that we require a transmission? Anybody? You can unmute and tell me as well. Quickly, but we don't have much time. So quickly. Anyone?
To accelerate and deaccelerate.
To accelerate and deaccelerate. Okay, interesting. And thank you. Anybody else? Why do we need transmission? Okay, there is a...
we can increase the torque.
Great. Okay, variable torque, speed according to conditions. Fantastic. Shreyas.
Torque distribution.
Fantastic. Awesome. Great. I got
way to wide range of speed.
Okay. Awesome. Great. Cool. So I got some answers from all of you guys. Good to hear from them. Anybody else have to answer? No. So now let's go back to the basics. Let's say that you want, so could you please unmute somebody? Submute. So let's say this is the graph for a motor, right? And this is the graph for an IC engine. Now, let me first draw the graph for... Okay, let me just draw the graph for a vehicle track to requirement. Okay, all of you, if you assume or imagine that you are driving a bike or driving a car, right? So when you imagine the okay, 1 second, I have to text this. Okay, this axis is basically the torque, right? And the other axis is, right, time. Okay, if you imagine for a first 30 seconds of your riding condition, what will be the torque value? Will it high? Will it be low? Anybody? Right? It will be high. So slowly when we rise when we go and driving the vehicle, then slowly the torque will come down. It depends upon if the road is open, flat, all this kind. If the road is up, then obviously the torque will increase, right? Imagine the road is flat. There is no signals. There is nobody coming and in front of you or something like that. The road is flat, right? And you're riding your vehicle. So obviously you require more torque in the beginning and gradually the torque will reduce, correct? So now let's all of us understand that the torque will be high, gradually the torque will decrease, right? This is a typical characteristics of the vehicle torque. It means this is what you need to supply to the vehicle. If you supply this to the vehicle, then the vehicle will move. I think everybody is in agree, right? So now let's go to the next thing. What is the torque characteristics of the IC engine? Anybody remember from your college days that what is the typical torque characteristics of the IC engine? Anybody know? Right. So if I have to just show you, maybe let's just go. Okay, I can't show. So the torque characteristics would come something like this, right? So the torque will be going high and then it will slowly come down. Okay. So now the vehicle requires the one in black as a torque, but the engine produces this as a torque, correct? So now vehicle will not be able to move if you just connect your engine's output to the wheel, right? So you have to increase the torque. So that's why what we do in realistic conditions, that we will be able to use a transmission in such a way that we will be able to create a torque like this, right? The first gear, second gear, third gear, fourth gear, and a fifth gear. In the fifth gear, we need a lot of RPM, right? You need less torque. So the RPM is required also more. Now, this is a problem with the IC engine because the engine cannot produce enough torque in the beginning, so you have to rely on the lot of transmission gear ratios. But when you see the torque of a electric motor, right? Torque for the electric motor. So if you might have already seen yourself in many conditions, the torque of an electric motor will come something like this. Okay. Sorry, this diagram is too much clumsy. I'm just going to erase some of these points. Oh. Okay. Yeah. So cool. So the torque of the electric motor would come something like this. It means the torque is very high in the beginning and then the torque will slowly come down. So when you say this is a typical torque characteristic of a motor. Now if you say, can I connect the motor directly to the vehicle or a wheel? Yes or no, right? So it means the torque is very high for the motor at the beginning and then it will gradually come down. If you compare that with the tractive requirement of the vehicle, it almost matches. That means that's why you see in many vehicles, electric vehicles, the motor is in the wheel itself, hub motor, correct? It means the motor has enough ability to drive the vehicle. It means the torque of the motor is very, very high so that it can drive the whole vehicle without a transmission. So that's why you can skip transmission in electric vehicles, but you cannot skip transmission in petrol or diesel vehicles. Is it clear? Right? So because the torque output of the motor can match the torque output of the tractive demand of the vehicle. The IC engine will not be able to do that. That's why you need transmission gear ratios for IC engine. But in some cases, you also needed a transmission for the motor as well. But that motor transmission will not be big. It means you see in IC engine vehicles, right? You need like you need minimum about what? 5-6 gear ratios, right? In cars. In bikes also you use at least 5 gear ratios now, 5-speed gear ratios. But in electric vehicles, you may just use like to maximum 1 or 2 gear ratios, right? It means you can make the transmission very simple, very small in size. Clear? Any questions? Okay. So that's the same way, a lot of components will also combine and submerge together. And I wish I could cover all the topics today, but the thing is that there's a limitation of time, how much we can cover, right? We may have other 5 minutes to kind of quickly discuss across everyone. So the same way the motor controller will take care of controlling the motor's speed and motor's torque. Apart from the motor speed and motor torque, it also takes care of a lot of other parameters, maybe mode control, regenerative control, giving data to the display system to say what is the speed of the motor, so that we can calculate the motor speed, wheel speed, all these things. So like this motor controller takes care of a lot of operations, right? Even diagnostics, if there's a failure in the motor controller, it has to inform to that person. So like this way, the motor controller will be an effective system which will take care of a lot of activities to ensure that the motor will be working efficiently in all the possible regions. So the same way, the onboard charger is the one which is basically there to take care of charging the battery pack. So in continuation of the same thing, we also have other components such as DC-DC converter. Why do we use a DC-DC converter? The reason we use a DC-DC converter is, let's say there's a headlight, right, tail lights, all these things, and there's a lot of power windows, power mirrors. These components runs at 12 volts if it is a car, right? They will run at 24 volts if it is a commercial vehicle like truck or a bus or something like that. Okay, so it means you have to have a system because your battery pack is at a higher voltage, maybe like 48 volt, maybe like 150 volt, 200 volt, 450 volt, even 800 volt or 1000 volt is also there in the buses. So you need to convert something from higher voltage to a lower voltage, like something like 12 volt, 24 volts, basically depending upon your applications. So at these scenarios, you need a DC-DC converter, which converts the higher voltage to lower voltage, right? So then battery pack is a combination of cells, and then cells are formed into modules, and the modules are formed into pack. The battery management system is a device which takes care of ensuring the safety for the batteries or safety for the cells. Let me just go through some of the images for you, so it just gives you some amount of clarity. Right? You have a hub motors which sits inside a wheel. We also have a mid-drive motors, also called as a non-hub motors. So there's a lot of comparison between these two motors. When do we use it? Why do we use it? And all these things. So now, if you see transmission here, this is a motor from the Nissan Leaf. In this section, which you see here, the motor and a transmission is so small, right? If you see in IC engines, right, the transmission is big, but here the transmission is quite small. It's because it's basically, it just have a 2-speed or a 1-speed like that, basic reductions. Motor controllers, then the battery packs, I said it's a combination of cells to form a module, combination of modules to form a battery pack. So again, there's a lot of content in here. As a limitations, I'm not able to cover everything. We can suggest you where you can learn as well. So the next thing is the cell safety. So the cells are quite dangerous. You have seen some circumstances like this, circumstances like this. It is not that you can avoid 100%. There is no guarantee that it will never happen. It may happen as well, but it's only that how much we can ensure to reduce the occurrence of scenarios, right? So with that way, if I tell you, you can reduce the occurrence by keeping battery in a safer region. That is why we use a battery management system, which is basically a way to ensure safety for the battery pack. Then the chargers, we have onboard chargers. We also have a half-board chargers, which is like this. In terms of half-board chargers, there are a lot of technologies like GBT, CHAdeMO, and Type 2 combo IEC chargers, which is called as a combined CCS, combined charge standard, right? So it means they all have specific relative values that how much rate of charging that you can also use. So then obviously there's also other loads such as HVAC load and DC-DC converter load. Again, if you interestingly, right, if you have rode in a car, imagine you park the car, right, stop the engine, turn off the engine, basically, then try to press the brake. The brake will become harder, right? Why it becomes harder? Because typically all the brakes are assisted by engine's vacuum. Just try to turn on the engine, then it'll all become proper. You can easily press the brake. That is condition when, because the engine vacuum is used to assist the braking. The same way here also in electric vehicle, there is no engine, right? You can't get the vacuum. You need to use a different pump for actually the braking system. Again, in the heating and cooling also, if you know how the heating was done in IC engines, IC engine, the heat will be there, because it is running. There is a heat being produced, the heat being simply dumped into the environment. So you will take the heat into the cabin by having a heat exchanger. Okay, so you can exchange the heat between your engine and the cabin by creating a exchange system. But in electric vehicles, you may not have that source that is available for you, right? Even though there is a battery heat, there is a motor heat, but bringing that heat will become a interesting factor. So for this, we need to have a separate heating system also. We need to have a separate cooling system also. So like this way, there's a lot of difference between the IC engine and a electric vehicle components and stuff like that. I just give you a very, very surface level overview on what these components and systems are. If you have any questions, the floor is open for QA. You can also unmute and ask. Which cell is best for racing applications? See, I mean, nowadays, even cylindrical cells have a higher discharge rates as well. It depends upon whether you can get the cell. Okay. Today, it is not like, okay, I want a pouch cell, I want a cylindrical cell. You should have a supplier even to send you that cell, right? So you can buy it. So it just not that, okay, you can just have the cells. Prismatic is out of the case. Obviously, you can use between cylindrical and pouch, but just do check which one is available. How to control the current increased in winding when the load increases? So you could have a motor controller. That is a functionality of a motor controller. It lets the more amount of current depending upon the load on the motor. Any other questions? Okay, so good to see that you have enjoyed the session along with all of us. So any other questions? So what speed gear ratio of one speed gearbox will retrofit? What is gear ratio of one speed gearbox will retrofit? I'm sorry, Atul, I didn't quite get the question. So you can please repeat the question. Anybody have any questions? Okay, great. So if you don't have questions, no issues. I believe I was able to deliver the session effectively for all of you. I believe you guys, it was useful for you, that it was also informative for you. I believe you have been able to take away some amount of learning from the beginning of the session and last like about 45 minutes to 1 hour. So let us know before you, that's it for today, what I can cover as an overall session. Let us know if you had any good learning experience in today before you exit the meeting as well. By the way, yeah, somebody who is exiting, and that's the end of today's sessions. Thanks a lot, everybody who have been participating in the session today. And tomorrow we will have an interesting hands-on calculation session where you'll be able to learn about motor power consumption calculations. Yes. So fuel cell, yeah, right now it is out of the topic as a fuel cell. Okay. Gear system used to EV more than a torque. Okay. I'm sorry, Lakshmi, I didn't quite follow the questions from your side. Awesome. Then I think, guys, if it was useful for you, thanks a lot again for participating in the session. It was always great to interact with all of you again and again. You can just find our YouTube channel here. If you see that the session is still getting live streamed, you can definitely go and check out the video. If you have any questions or if any doubts are there, the video is right here. Okay, so it's just being live streamed as well. So if you have any queries, as I said, you can still go and check out the video for any of your clarifications as well. So that's it from my side, and thanks a lot, everybody, for attending today's session and showing all of your interest to interact with all of us. Thanks again to all of you.